Greeting everyone, a pleasant day. We are Group A and we are going to present 3 problems from Chapter 10 Vapor-Liquid Equilibrium of the textbook Introduction to Chemical Engineering Thermodynamics. The members of the group is me, Harvey Ang, Angel Rabullo, Marque Kilan, and Kate Villalobos. Hi, I'm Harvey J. Tiang and I would present problem 10.19. For our problem, we are given a binary system of species 1 and 2 consisting of a vapor and liquid phase in equilibrium at temperature T, for which ln gamma 1 is equal to 1.8 x sub 2 squared and ln gamma 2 is equal to 1.8 x sub 1 squared, in which x stands for the molar fraction in the liquid phase and gamma stands for the activity coefficient. We are also given with a saturation vapor pressure of species 1 to be 1.24 bar, while the saturation vapor pressure of species 2 to be 0.89 bar. Assuming the validity of equation 10.5, we are asked to find for letter A for what range of values of the overall mole fraction Z sub 1 can this two-phase system exist with a liquid mole fraction of species 1 to be 0.65. For letter B, we are asked to find what is the pressure P and vapor mole fraction of species 1 within this range. And lastly, we are asked what are the pressure and composition of the azeotrope at temperature T. Here is the summarized form of our given. For our solution for letter A, we are asked to find the range of Z1 in which the two-phase system could exist given x1 to be 0.65. So we could find this by using an expression of the amount of V by using material balance given the expression Z1 minus x1 over y1 minus x1, where the value of V ranges from 0 to 1. However, we don't know the value of y1 or the amount or the mole fraction of species 1 in the vapor phase. Therefore, we can now proceed to part B to solve for y1 first. To solve for y1, we could use equation 10.5 from our textbook, Introduction to Chemical Engineering Thermodynamics, where we could use the modified Raoult's law shown below. We could solve for P then by using equation 10.6, which is a modified form of the Dalton's law. Then to get for gamma 1 and gamma 2, we know that ln gamma 1 is equal to ax sub 2 squared and ln gamma 2 is equal to ax1 squared. These values are given, so we would just modify this. Then we could get gamma 1 to be 1.2467 and gamma 2 to be 2.1393. Then we substitute gamma 1 and gamma 2 to P. Then we could get the value of Rp to be 1.671 bar. Next, we substitute P to Y1 using the modified Raoult's law. Then we would get Y1 to be 0.6013. Now going back, we could solve for part A. So for using our material balance equation, when V equals 1, we could get that Z1 is equal to 0.6013. When V equals 0, we could get that Z1 is equal to 0.65. Therefore, the range of our Z1 is in between 0.6013 and 0.65. For letter C, to get an azeotrope, we must met the condition x1 is equal to y1. We know that from our modified Raoult's law, we have this given expression below. Since x1 is equal to y1, the equation simplifies as y1 times the saturation vapor pressure of 1 is equal to P. This is also true for x2 equals y2. Therefore, equating them, we could get this expression. We know that gamma 1 is equal to e raised to ax sub 2 squared and gamma 2 is equal to e raised to ax sub 1 squared. Therefore, our equation simplifies to this equation. So modifying this, we could get this expression, and then the value for, we know that the value for the saturation vapor pressure of species 2 is equal to 0.89, and the value for the saturation vapor pressure of species 1 is 1.24, which gives us a value of 0.7177. The equation then simplifies to this expression. We know that the value for A is equal to 1.8 from our given. We could further simplify the expression x sub 2 squared minus x sub 1 squared. We know that we could simplify x squared minus y squared in this form. X sub 2 minus x sub 1 times x sub 2 plus x sub 1, where we know that x sub 2 plus x sub 1 is equal to 1, since the only composition in the liquid phase is just species 2 and species 1. Hence, x sub 2 squared minus x sub 1 squared is just equal to x sub 2 minus x sub 1. However, we could also simplify x sub 2 to be 1 minus x sub 1. Therefore, the final form for x sub 2 squared minus x sub 1 squared is just equal to 1 minus 2 times x sub 1. So substituting this value in our expression, then simplifying it, we would get that x1 is equal to 0.592. Since x sub 1 is equal to y sub 1, then y sub 1 is equal to 0.592 as well. Solving for p, we could use any form in our simplified expression. So we have e raised to a sub x sub 1 squared, then the vapor pressure of species 2, the saturation vapor pressure. Then substituting the values, we would get that the value for P is just equal to 1.672 bar.
For this problem, assuming the validity of the D-Brister charts, make the following VLE calculations for the ethane, propane, isobutane, isopentane system. As you can see below, we are asked to find the bubble point pressure, dew point pressure, bubble point temperature, and dew point temperature with their respective mole fractions and their intensive variables. So here are the given values in the problem. Also, we make use of the D-Brister chart found in a textbook in order to find the needed K values. Moving on, to find the bubble point pressure for the given temperature of 140 Fahrenheit, we find by trial the value of P, for which the K values satisfy the equation summation of K times X equals 1. Results for several values of P are given in the following table. As can be seen in the table, at 200 psia the summation is equal to 1.012, which is approximately equal to 1. Thus, the equation is satisfied when P is equals to 200 psia. This is the bubble point pressure. Next, to find the dew point pressure at 140 Fahrenheit, we find the value for which the equation summation of y over k equals to 1 is satisfied. By trial, it can be seen that the summation at 230 psia is approximately equal to 1, which is 1.03. Thus, the equation is satisfied when P is equal to 230 psia. This is the dew point pressure. Furthermore, to find the bubble point temperature at 220 psia, the same process in solving the unknown in letter A is applied. As can be seen below, the equation of the summation of x times k is satisfied when T is equal to 150 Fahrenheit. Lastly, to find the dew point temperature at 220 psia, the same process in solving the unknown in letter B is applied. It can be seen also that the equation of the summation of y over k is satisfied when T is equal to 150 Fahrenheit.
Problem 10.33, presented by Mark James Hilan II and Kate Claire Villalobos. The top tray of a distillation column and the condenser are at a pressure of 20 psia. The liquid on the top tray is an equimolar mixture of N-butane and N-pentane. The vapor from the top tray, assumed to be in equilibrium with the liquid, goes to the condenser where 50 mole% of the vapor is condensed. What is the temperature on the top tray, and what are the temperature and composition of the vapor leaving the condenser? The given are pressure of 20 psia, and since it is an equimolar mixture, the mole fraction of N-butane is 0.5 and the mole fraction of N-pentane is 0.5. The vapor phase in the condenser is 50 mole%. The required are the top tray temperature and composition of vapor leaving the condenser. Assumptions: no chemical reaction in the mixture, vapor phase is in equilibrium with liquid phase, and constant pressure at 20 psia. To determine the temperature at the top tray, equation 10.13 should be satisfied. The summation of Ki times Xi is equal to 1. For our Xi, or the mole fraction, is given in the problem, which is an equimolar mixture of N-butane and N-pentane, giving 0.5 value each. We will get our K values from the Brewster chart at a pressure of 20 psia. For our first trial, we assume temperature of 65 Fahrenheit or 18.33 Celsius. We get the K value for N-butane and N-pentane to be 1.498 and 0.420 respectively. For the vapor phase at top tray, we use equation 10.10, and deriving this equation, we get Yi is equal to Ki times Xi. For N-butane, K value multiplied by its molar fraction, we get 0.749. For N-pentane, using the same process, we get 0.21. Summing them, we get 0.959, which is not close to unity, meaning we need to assume higher temperature for the next trial. For the second trial, we assume 70 Fahrenheit temperature or 21.11 Celsius. Using the Brewster chart at pressure of 20 psia, we get the K value for N-butane and N-pentane to be 1.526 and 0.460 respectively. By doing the same process from trial 1, for N-butane and N-pentane, we obtain vapor phase values of 0.763 and 0.23 respectively. Summing these values, we get Y is equal to 0.993, which is close enough to 1. Thus, we can say the temperature at the top tray is 70 Fahrenheit or 21.11 Celsius.
Since some of the vapor is condensed to liquid, flash calculation will be used. From the calculated vapor composition in the top tray, the overall composition in the condenser is 76.3% N-butane and 23% N-pentane. To determine the temperature and composition of vapor leaving the condenser, equation 10.17 should be satisfied. The K values is determined using the Brewster chart at certain temperature and pressure. Since pressure is constant at 20 psia, the temperature will be assumed to be 70 degrees Fahrenheit in the first trial. From the chart, the K values for butane and pentane are 1.526 and 0.46 respectively. The vapor phase composition in the condenser can be calculated using equation 10.16. On the basis of 1 mole unreacted mixture in the condenser, the vapor consists of 92.2% B and 14.5% P. The overall vapor phase composition is 1.067 which is still not close to unity. For the second trial, the temperature of the vapor is assumed to be 60 degrees Fahrenheit. Temperature should be lower than the first assumption in order to condense some amount of vapor. Thus, we will be getting a value of y closer to unity. The K values from the pressure chart at 20 psia and 60 degrees Fahrenheit is Kb equals 1.35 and Kp equals 0.37. Using equation 10.16 to calculate the vapor phase composition, in which 87.7% is butane and 12.4% is pentane. This leads to the overall vapor phase composition of 1.001, which is very close to unity. Therefore, the vapor, having approximately 87.7% of N-butane and 12.4% N-pentane, leaves the condenser at a temperature of 60 degrees Fahrenheit.